Hello there A&P2 students, it's good to see you again. In this video we will be taking a look at gas exchange and some of the factors that influence it. Now we all know the way the story ends. The hero gets the girl. Oh sorry, that's the wrong story. The tissue cells get the oxygen and carbon dioxide is kicked out of town. We're going to start our discussion at the respiratory membrane, but before we do, let's go over some basic information that you need to know. Gas exchange is a process of diffusion that is driven by pressure gradients, and how quickly and effectively these gases move depends on two factors: the partial pressure of the gas and its solubility. The law of partial pressure states that the total pressure exerted by a mixture of gases is the sum of the pressures exerted by each independently. So each partial pressure is a part of the whole, and partial pressure can be expressed as either a percentage or as millimeters of mercury. If we take the partial pressures of the four main gases that make up air, we can see that the majority of air is made up of nitrogen and oxygen. And at 1 atmosphere, their partial pressures in millimeters per mercury should add up to 760 millimeters of mercury. If we compare these values to alveolar air, we see an increase in carbon dioxide and water and a decrease in oxygen and nitrogen. You might wonder why there's such a big difference between alveolar air and inspired air. We know that inspired air mixes with residual air left in the lungs after exhalation. Well, it makes sense that the percent of CO2 in alveolar air will increase from that of atmospheric air, and also that oxygen will decrease. And if you know anything about respiration, well, it's that we breathe in oxygen and we exhale carbon dioxide. And that's partially true. We actually breathe in both and exhale both. But at the respiratory membrane, we are diffusing oxygen into the blood while we're diffusing carbon dioxide out into the air to be exhaled. And that's what's giving us the change in the partial pressures that we're seeing for both carbon dioxide and oxygen. What about this increase in water that we're seeing? Well, we know that the air is humidified as it enters the respiratory tract. As a matter of fact, it's humidified the whole way through the respiratory tract. We exhale a good amount of water vapor. Let's now take a look at nitrogen. Common sense would tell us that with such a large drop in partial pressure of nitrogen, that we must be absorbing a lot into our bloodstream. But the truth is we absorb very little. How can that be? Well, the reason we see such a drop in the percentage of nitrogen is not because there's less nitrogen in alveolar air, but because it is a piece of the pie, and its pressure is relative to the others. So as the partial pressure of one gas or piece of the pie increases, the other pieces of the pie have to decrease because they all must still add up to 100% or 760 millimeters of mercury. How well a gas will dissolve in a liquid depends on the gas's solubility. Some gases are more soluble than others. Carbon dioxide is 20 times more soluble than oxygen. So if we had carbon dioxide and oxygen at equal partial pressures and gave them equal time, much more of the carbon dioxide would dissolve into a solution. In other words, it would take much longer for oxygen to reach a state of equilibrium, which would be where the partial pressure in the air equals the partial pressure in the liquid. Well, this becomes an important consideration when we understand that blood is dynamic and it's constantly moving. So a red blood cell will have a limited amount of time spent at the respiratory membrane. Let's take a closer look at the respiratory membrane. We know that three structures make up the membrane, and these are the type 1 alveolar cells, which are simple squamous, the two fused basement membranes, and the endothelial cell of the capillary, which is also simple squamous. The thickness of the membrane in a healthy individual is between 0.5 and 1 microns, and this thickness allows for very efficient gas exchange. But anything that increases the thickness of the membrane will decrease this efficiency. In class, we talked about the huge surface area for gas exchange that's available in the lungs, which your textbook gives at 90 meters squared of area for both lungs. Remember the football field analogy. This is a huge amount of area for gas exchange, but anything that decreases this will decrease the efficiency of gas exchange. Now, a red blood cell will spend about 0.75 seconds in transit along the respiratory membrane, during which time it has to dump off carbon dioxide and take on oxygen. Now, this seems like a very short period of time, but under normal conditions, this is plenty of time for equilibrium for both carbon dioxide and oxygen to be met. You might be wondering that if oxygen is 20 times less soluble than carbon dioxide, how is it that equilibrium can be met for both within such a short period of time? Well, that comes down to their relative partial pressures and the pressure gradients. And we will see that the pressure gradient for oxygen is much more steep than it is for carbon dioxide. So let's look at these pressure gradients now. If we compare alveolar air to inspired air, we see a difference in the values for carbon dioxide and oxygen between the two. We've already discussed why alveolar air does not match inspired air. Now these values, which are in millimeters of mercury, are the ones that can be found in table 21.4. So take a look at that table right now and get yourself oriented with these numbers. Now that you understand where these values come from, what we want to do is compare the partial pressures of oxygen and carbon dioxide between the alveolar air and the blood entering the respiratory membrane capillaries. And that would be the deoxygenated blood leaving the heart through the pulmonary arteries. Notice the steep gradient for oxygen with a partial pressure of 104 millimeters of mercury within the alveolar air and 40 millimeters of mercury within the blood capillary. This steep gradient allows oxygen under normal circumstances to reach equilibrium within 0.25 seconds, much faster than the 0.75 seconds that the red blood cell spends at the respiratory membrane. So it is the large difference in these partial pressures that allows oxygen to diffuse so rapidly. And there's a much more gentle pressure gradient for carbon dioxide, but because of its enhanced solubility, it diffuses easily. Under normal circumstances, equilibrium will be reached with these two gases between alveolar air and capillary blood. Or at least they should. Well, let's take a look at the blood leaving the lungs through the pulmonary veins. If equilibrium was met, then these values should equal alveolar air. And carbon dioxide does, but oxygen does not. Can you think of a reason why the partial pressure of oxygen would be slightly lower than the expected value of 104 millimeters of mercury? We have been looking at external respiration, which occurs at the alveoli. At the other end, internal respiration is occurring at the tissue level. And there should be no mystery here if you apply the same principles as to what gases are moving where. I'll let you spend some time on your own with this information, and we'll talk about it in class. One important thing that I want to add to your understanding here is that at the tissue level, there will be an endless buildup of metabolic waste products. And these will be carbon dioxide, and along with carbon dioxide is hydrogen ions. And there's also a buildup of a molecule called BPG, or 2,3-bisphosphoglycerate. We'll be looking at these three metabolic byproducts, and we're going to look at how they affect hemoglobin's ability to bind oxygen. Please read about these three so that you are ready for that discussion. The last thing that I want to go over with you in this video is the various ways that these two gases are transported in the blood. I'm sure that this picture seems overwhelming for you, so I'd like to simplify what it is you need to know for now. Let's focus on oxygen, and we can see that oxygen is transported in two different ways. The majority of oxygen is bound to hemoglobin, and only about 1.5% of oxygen is dissolved in the plasma. And that makes sense since oxygen is not very soluble in water. Carbon dioxide, on the other hand, is more soluble in water, so a larger amount will be dissolved in the plasma. But the majority of carbon dioxide is converted to bicarbonate. And within the red blood cells, this reaction is very fast because of the action of the enzyme carbonic anhydrase. And the third way that carbon dioxide is transported is bound to hemoglobin. Now remember, carbon dioxide binds to the protein portion of hemoglobin, whereas oxygen binds to the heme. And these two gases have different effects on hemoglobin, changing its shape. We will talk about how important these changes are to hemoglobin's ability to load and unload oxygen at the appropriate times. So I hope I've given you a lot to think about and to get you ready for our final lecture on the respiratory system. So I'll see you in class.